Hello again. Yes, it's your friendly heavy physics teacher once again here with a Regents Physics lesson. This is for my Regents Physics class, Unit 10, Lesson 4. We're talking about electromagnetic induction as it relates to generating electricity. And this is most often how people use the term electromagnetic induction. They're talking about when we're actually generating electricity, or we use a magnetic effect and it's going to affect the electricity in a conductor. Okay, so the essential question for us today is, how does the interaction of a conducting surface with a magnetic field, how does that produce electricity? Alrighty. Alrighty, we're going to start off with a demonstration before I get into my whiteboards with our definition stuff on it. Okay, hopefully you've got the notes that I've asked you to download. All right, but here we go. I've got a coil of wire. All right, and what I've done is I've wrapped about 50 turns of wire onto this old paper tube here. Okay, and magnet. Okay, and I'm going to take the North Pole and I'm going to move it through the coil of wire. I want you to watch the needle over here on the galvanometer. See that? Notice it did something else when I pulled it back out. All right, so putting it in, pulling it out, putting it in. All right, notice that the direction of motion of the magnet is creating a certain direction of current in the wire. Notice that if I flip the magnet around, I'm reversing the direction of current. Okay. Now, what if I move the wire instead of the magnet? Okay. Notice it doesn't matter which is moving. And notice that if I move them at about the same speed, I'm getting the same amount of deflection over here on my galvanometer. Okay, so we have the idea that the magnetic field moving relative to a conducting material is generating electricity in the conducting material. And this is at essence what we call Faraday's law, that the relative change in magnetic field intensity near a conductor will induce an EMF, a voltage, a potential difference across the ends of the conductor. Okay? Now, notice if that there can be a maximum interaction, right? I'm not really getting much of an interaction. There's a little bit, but I get a maximum when I go through the enclosed area created by the coil of wire. Okay? Now, watch what happens when I increase the amount of magnetism that's there. Okay? I take two magnets, make sure that both have the same pole the same way. Notice I get a much bigger deflection moving it at the same speed. All right? Let's up the ante. Okay? I'm going to quadruple the magnetism that's there. Relatively hard to hold them all together. See, I'm getting a really large change in the deflection. Okay. Now, what if I take and I do this with a different number of coils of wire? Okay. What if I went down and I just did one coil? If I had one loop of wire, would it create a deflection over here? Obviously, the answer is yes. okay? But the amount of deflection would be considerably less than what it is here, all right? Essentially, it'd be 1/50th. If there's 50 turns of wire here, then the amount of deflection would be 1/50th of that, since it would be only one loop of wire. All right, watch what happens when I increase the amount of wire. Now you can't see it, but the reason you can't see it is I've had to wrap masking tape around this so that the wire doesn't come flopping off. All right, but I've got about 200 wraps of wire on this particular coil. All right, and so if I take one magnet and move it, notice that that's considerably larger than this one over here. Okay, two magnets. Notice I've got about as much as I had four magnets the last time. Okay, go with four magnets. See, I'm almost getting full scale deflection here, especially when I move it hard. Okay, so what's creating the EMF? And what's this EMF thing I'm talking about? Okay, EMF is an archaic term for voltage. We'll get to that in a little bit. All right, you should have seen that on the notes page. All right, when you have a conducting material, in this case the copper wire, and it moves relative to a magnetic field. So it could be the magnetic field that's moving, it could be the copper wire that's moving, or you could have both of them moving relative to each other. You are going to produce a voltage across the ends of the wire. And if that is connected to some other load, some other device, then you are going to get a flow based upon that voltage. Okay? We have a relatively small flow because this has a relatively low resistance. So the available voltage is going to produce a relatively small current. Okay? I'm not generating a lot of volts here, probably on the order of maybe 0.01 volt is being generated by this. Okay? But we're still generating electricity. You see how if I scale this up, if I make this huge, if the magnets I use are very large, okay, it doesn't have to be very strong, but they're large enough to fill this space, that I could scale this up to the point where I could produce thousands of volts of energy, thousands of volts of electric potential. Okay? So, what are all these terms I'm throwing around, and how do we determine how much electricity we generate? Okay, generating electricity. All right. When a conductor moves through a magnetic field, or the magnetic field changes, the magnetic field itself could move, or itself could change in some fashion across an area of a conductor. That relative change between these two create the EMF. They create the potential difference or voltage across the ends of the conductor. Okay, and this is what we call Faraday's law. This was his great contribution to our understanding of electricity. The idea that you could make electricity from magnetism by moving a magnet relative to a wire. Okay, he did a very interesting experiment to prove that way back in the 1830s. Okay, now soon following up on that, we began investigating, how do we know which way the current's going to flow? How do we know how much current's going to flow? Well, a lot depends on how much energy you actually generate. And a Russian scientist by the name of Lenz came up with a relationship about that. Lenz's law is kind of like Newton's third law for electromagnetism. Okay, Lenz's law. An induced EMF in a conductor will create a current that makes a magnetic field that opposes the original magnetic field that caused the EMF in the first place. In other words, you don't get something for nothing. Okay? So, if I were to actually measure how much force I was pushing the magnet through the coil with, I would also notice that I would feel that amount of force exerted back on the magnet caused by the current, creating its own magnetic field opposing the magnet that I'm pushing through it. Okay? You can't get something for nothing. All right? That's all that Lenz's law is implying here. That's all that this is stating about this principle. If you're making electricity, then the electricity that you make creates an oppositional force, which is why when you push on something in a generator, that generator pushes back against you. Okay? And so there's no free energy. This is what's making us makes it obey the conservation energy laws. All right? If I'm putting work in, then it's going to take that work away. You're going to feel the resistance of it take the work away to turn it into electricity. Got it? All right. Okay. Here's how we calculate how much electricity that a changing magnetic field or the motion of a conductor in a magnetic field will generate in that conductor. Okay? So we use this script letter E here to represent something called EMF. It's electromotive force. It's an archaic term for voltage, but we keep using it because when someone says, what's the induced EMF in that generator, you are automatically thinking, oh, okay, I've got a changing magnetic field, I've got a conductor moving around, da 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 da. So that's where the voltage is coming from. There's a change happening. Okay? So the amount of voltage, the EMF, is equal to the change in magnetic flux. That's what this symbol, the Greek letter phi, means magnetic flux. More on that down here in a moment. Okay? And how much time it takes that change to take place. Okay? If you get no change, you're not going to generate an EMF. You're not going to generate a voltage. That's why it was when I moved the magnet through the coil that we got a deflection. But if I just sat there with the magnet inside the coil, nothing would happen. It wasn't until I pulled it back out that a change happened. It happened in the opposite direction. Okay, magnetic flux, all right? It's equal to the magnetic field intensity times the area of the exposed conductor to that magnetic field. Interestingly enough, you get a maximum amount when the area is fully exposed. So there's some very interesting ways to create change in flux. One of them is to turn something sideways. Okay, so here might be my hand might represent the exposed area. Flip my hand sideways, and now the area is considerably smaller. So it's this change from here to here is the change that might be this. Flip it around again. Boom, boom, boom. You see how if you continuously create a rotation of a loop of wire, you can create a continuous change that's going on. So you'd create a continuous voltage. Interestingly enough, every time you flip it 180 degrees, the direction of the current switches. Oh, wait a minute. Isn't that the problem we had with motors, and we had to deal with that? Same thing with an electric generator. The parts of an electric generator are identical to the parts of a motor, and in an emergency, you can use one as the other. Okay? So, EMF, voltage, is equal to the change in the flux. And the flux is dependent on the field intensity and the area exposed. Obviously, if you loop 2 wires, this becomes double. You loop it a third time, this becomes triple. You loop it a fourth time, so on and so forth. So the number of loops also determines, it has a factor on how much area is exposed. More loops, more area. The number of loops multiplied by the area gives you the total area exposed to the magnetic field. Okay? On that, the class notes, you will see on the back that there are example problems. Okay? The example problems go with the equations that I just gave you, as well as all of our other equations for this particular unit. I will be providing an answer key for them tomorrow, maybe the day after, so that you can go back and look at them and see how to do the calculations. Okay? So there we are. Electromagnetic induction. It can either be a motor, where you have a conductor in a magnetic field and you push a current through that conductor, and it's going to cause the conductor to flip relative to the magnetic field. Okay, so you are inducing a force on the conductor. Or if you have a conductor in a magnetic field and you create relative change, either by moving the conductor out of the field, pushing the conductor into the field, or rapidly changing the field on its own, say with an electromagnet, turning it on and turning it off, that creates a magnetic field and then collapses the magnetic field. That changing magnetic field relative to the other conductor induces an EMF. So it's the principle on which electric motors and electric generators both operate. Okay? My next video lesson is going to be about how we use transformers and how they use this electromagnetic induction principle in order to be able to allow us to transmit energy, electrical energy, over long distances with relatively small losses through those transmission lines. This is your friendly heavy physics teacher signing off one more time. Hopefully we get back to school soon. All right. See you later, buddy. Folks. Bye-bye.